This is a Pulse Instruments focal plane test system, suitable for imaging, test, and characterization of a wide variety of infrared and visible imaging devices. It is a flexible, high-performance test system designed to meet the demanding needs of scientific research and production test applications. A typical system will consist of one or more instrument mainframes with instrument cards, such as a CPU card, pattern generator cards, clock driver cards, low noise bias supplies, A to D timing and control, digital multiplexer, and digital acquisition cards. The system will also have one or more analog interface modules, or AIMs, which contain gain and filter boards and A to D converter modules. The digitizer boxes also have controls for the external preamplifiers, which apply gain and DC offset correction to the video signals. The preamplifiers are supplied in small aluminum enclosures at the end of 5-foot cables, which allows them to be placed very close to the device under test. This can be critical for ensuring low noise performance. For this demonstration, we will be digitizing a test pattern. These clock signals would ordinarily be driving your device. Instead, we are going to feed these into the preamplifiers and digitize our own signal. If I remove the input from preamplifier number 1, you can see the left quarter of the image go blank, and when I plug it back in, the image reappears. We are creating this moving image with our pattern generator and clock drivers and displaying it in real time. With Pulse Instruments flexible pattern generators, we can edit the device timing in real time while the device is running, and while we are collecting data. In this example, I will edit the timing file to blank out several pixels of the sample pattern. As I zoom in on the display, you can see that several of the pixels in the border are now dark. I can then return to the pattern editor, click Undo, and restore those pixels. This is far simpler and faster than reprogramming an FPGA. With an FPGA, you would have to shut down your device, pull out the EEPROM, recompile your VHDL, program the EEPROM, and turn your device back on. By the time you've finished that cycle, you probably will have forgotten what you were trying to do. With the Pulse Instrument system, it takes just a few seconds to adjust the timing and see the effect on my device's performance in real time. The system also has monitor outputs, which allow us to see the actual analog waveforms that we are digitizing and the point in time when we are sampling. Shown here on the oscilloscope, the green trace is our video stream and the yellow trace is our sampling clock. The scope shows 1 pixel period of the video waveform. The video signal has a constant high region, a constant low region, and a region that is intermittently high and low. This is the region that is flickering on the oscilloscope, and it is the place where we want to sample the video. This is similar to a typical CCD output that has a reset feed-through, a reset pedestal, and an information well. As you can see, we have real-time control over the timing relationship between the rising edge of the sampling clock and the video pixel period. We can place the sampling point anywhere within the pixel period, with a resolution as fine as 100 picoseconds. We also have real-time control over the gain and offset of the video signal. We can apply up to plus and minus 10 volts of DC offset correction. In this example, I can drag the signal into saturation on the negative side or the positive side. In your application, you would use this feature to center your video signal into the range of the A to D. Here, looking at the video signal, we see the results of the same operations. First, moving the conversion point in and out of the information well, and then moving the DC offset into and out of saturation. We also have gain in the system, from 1x to 420x, to maximize use of the A to D's dynamic range, and also to detect very small signals. Within the data acquisition system, I also have flexibility to turn each of the channels on and off. The digital multiplexer card is also a 4-to-1 switch, so I can use my software controls to turn each of the channels on or off. I can look at any one of the 4 channels, or I can say 2, 3, or 4 channels stitched together. This is useful for testing CCDs and focal planes that can output on 1, 2, 4, 8, or 16 outputs, depending on how they are clocked. We can also define how the outputs are plotted, allowing us to rotate, flip, and interleave the display. In this example, Video channel 1 is being plotted to columns 1, 5, 9, 13, etc., which is a very common output format for infrared devices. This is the focal plane definition control, which allows the user to specify which channels are on or off and how to reassemble multiple channels into a single image. Next, we have the data acquisition controls, where we control how many frames to acquire, the data format, file name, etc. For real-time imaging, we are just capturing one frame at a time and displaying it as fast as we can. We can also collect multiple frames. For example, here we are collecting 32 frames of this moving image and averaging them together. We can have up to 512 megabytes of acquisition memory per card, and we can stack up to 8 acquisition cards in a system to provide up to 4 gigabytes of uninterruptible acquisition memory. This sample pattern is 256 by 256, and we store 2 bytes per pixel, so we can collect up to 4,096 contiguous frames of data into this single 512 megabyte card. Once the data has been DMA'd to CPU memory, we can play it back or examine any particular frame. This sample pattern was designed to move the logo by exactly 1 pixel on each successive frame. So by paging through the file, 1 frame at a time, we can verify that we have captured all 4,096 frames without missing a single frame or a single pixel. This highlights a key difference between our data acquisition cards and a typical off-the-shelf frame grabber. The typical frame grabber has a small amount of onboard memory, so during acquisition of high-speed data, it's a race to unload the card onto a disk system. You have to worry about bus contention, operating system latency, CPU loading, etc. Our data acquisition cards have large onboard memories, and the collection process runs entirely on the card's firmware. During the data collection process, you don't have to worry about bus contention or the operating system because nothing will interrupt the acquisition cycle until it's done or until the operator presses stop. Our cards can handle nearly any standard or non-standard readout format, and there is no limit on how long the card will wait for data. Even if your device reads out continuously, as many focal planes do, you will not drop any pixels or any frames using our system. You can collect all your reference rows and columns, which can be very important when doing frequency domain noise analysis. Now let's move on to a demonstration of our automation features. Previously, we showed how the placement of the conversion strobe can be controlled manually. This time, I'm going to run an automated test plan. This test plan sets up 100 loops. On each loop, it will step the convert strobe position by 1% of the pixel period, collect 32 frames of data, calculate signal amplitude, calculate pixel noise, and report signal-to-noise ratio. Once the 100 loops are completed, the system will report the convert strobe position that results in the best signal-to-noise ratio. It will also export the entire dataset to Excel so we can see a graph of the signal, noise, and signal-to-noise ratio against the convert strobe position. This type of parametric sweep can be done for integration time, illumination level, wavelength, black body temperature, bias voltage, clock rise time, etc. This enables a tremendous amount of flexibility in characterizing device performance across a wide range of operating conditions and parameters. Best of all, once the test plan has been set up, you can click Go, have lunch, and return to the system once the data has all been collected and assembled into a report. Now I will load some actual data that was collected on one of our systems recently. This is 1,000 frames of raw, uncorrected imagery from a 320 by 256 infrared device. As you can see, there was a large amount of fixed pattern noise and non-uniformity, as well as a large number of dead pixels. In addition to the 1,000 frames of live video, we also have 32 frames of the device looking at a hot reference and 32 frames of a cold reference. We could use these to calculate sensor performance and also to build image correction tables. First, we will count bad pixels. As you can see in this test plan, we have a graphical analysis feature that allows mathematical analysis without writing any code. This example uses a threshold of 3 sigma from the mean to determine which pixels are bad, but you can use any threshold value or voltage that you want, depending on the characteristics of your device. When we run the test plan, it tests each pixel's responses against these thresholds, then marks each bad pixel location. It can also read the temperature from the blackbody controller and use this to calculate responsivity and NETD. When the test plan is finished, it can output the bad pixel table to Excel with the address of each bad pixel and the address of each good pixel used to replace it. We use a spiral search algorithm to find the nearest good pixel. We can view the bad pixel map and report in our PyPlot software. Good pixels have a value of 0, and bad pixels have a value of 1. The number of bad pixels is reported, as well as the operability of the device. We can also report the number of bad pixels in a key region of the device, such as the middle quarter. Let's pull up the NETD map in PyPlot. Let's pull up a histogram view and increase the contrast. We can set the black point and the white point, then return to the grayscale plot and maximize the contrast. In this example, we were aligning the lens by hand, so you can see the result of some misalignment. Next, we can count clusters of bad pixels. If we define a pixel as having 8 neighbors, we can calculate each bad pixel's cluster count as the sum of all its neighbors. We run the test plan, and it reports clusters of size 1, 2, 3, etc., up to 9. We can display the cluster map in color, then zoom in to see the different cluster values at each location. Now, we can use the hot reference, cold reference, and bad pixel table to do a correction on the acquired video. I'm going to load the corrected video file, which has had a 2-point non-uniformity correction, or nuke, applied, as well as bad pixel replacement. If you compare this to the uncorrected video, you can see that the fixed pattern noise is completely removed, as are most of the bad pixels. There is a large cluster in the center left region that goes into saturation and cannot be fully corrected. Now that the fixed pattern noise has been removed, I can do a proper histogram correction. Again, I pull up the histogram display, set the black and white points, then return to the grayscale display. With the contrast maximized, the video looks much better. I can also view this in false color mode. PyPlot supports export to common still image formats such as bitmap, JPEG, and TIFF, and video formats such as AVI. Here we can see a 2-up comparison of uncorrected and fully corrected video in false color. Here at Pulse Instruments, we refer to the left half of the display as the engineer's video, and the right half as the chairman and CEO's video. All the video correction we've shown you thus far has been done in post-processing after the video was collected. We can also apply the correction in real time as we're acquiring live video. I'm going to use my test pattern again, but this time I'm going to program each of the 4 clock driver channels with different amplitudes and offsets to demonstrate offset and gain non-uniformity. As you can see, the image is very non-uniform. I have a test plan to collect 32 frames of cold reference, 32 frames of hot reference, and also to read in a dummy bad pixel table. Once my tables have been created, I can then apply the 2-point nuke in real time, and the image now looks uniform. I can also apply bad pixel correction, although in this sample pattern there are no bad pixels to correct. Another important feature is the ability to send serial command words to your device from the pattern generator. This is important for certain focal planes and CMOS or APS devices that are programmed through a serial input pin. These pins can control gain, windowing, and various other features of the device. I'm going to run the same test pattern that I've been using, and this time I'm going to load a different serial word into one region of memory on each loop. If you look at the pattern memory here, you can see that the values are changing on each loop. This can be used to perform a parametric sweep of integration time, on-chip gain, windowing, binning, or any other device parameter that is controlled by a serial word. Now let's look at noise performance. I'm going to use the timing from my test pattern, but instead of digitizing my pattern, I'm just going to short the input with a 50 ohm terminator. As you can see in the histogram view, the 1 sigma noise is just about 1 lsb. When we look at it in the grayscale view, with the contrast maximized, the noise looks random, with no visible periodic component. Here is an example of the system's ability to acquire very small signals. This is the same test pattern, but now the signal amplitude has been attenuated down to 6 microvolts peak to peak, and the image is not moving. We acquired 2,500 frames, then averaged them together. The video file I'm showing you now has been post-processed so that frame n is the average from frame 1 to frame n of the original raw data. In other words, frame 100 is the average of 100 frames from the original data file. As we play through the file, we can see the random noise being averaged away as more frames are averaged, and the constant signal comes through. The difference between light and dark is 6 microvolts at the preamplifier input.